Welcome to Transmission Media and Antenna System. In this lesson, we'll talk about loopstick antenna. The little antennas inside the radios are called loopstick because they are made from loops of fine wire wrapped around a rod of ferrite material. We'll also talk about history, different types of loop antenna, small loop antenna and its examples, ferrite rod antennas, and AM/FM antennas. History. During World War II, the loopstick antenna was developed in Germany. It consisted of a cylindrical plastic tube filled with powered iron, which served as a magnetic core, with a coil wrapped around the core near the center of the core. It may have been based on the work of Polidorov 1941. He patented a loop with a hollow ferromagnetic core, with the core length roughly twice the core diameter. This is an example of Polidorov loopstick antenna. A short ferrite loopstick antenna for aircraft. Note that it uses a hollow core. This antenna lab ferrite loopstick was apparently the first. Of course, they are now widely used in portable electronics devices. A typical loopstick antenna with a distributed winding. The winding can also be short, multilayer, concentrated at the core center. Loopstick antenna. Loop antennas feature simplicity, low cost, and versatility. They may have various shapes, circular, triangular, or square. They are widely used in communication links up to the microwave bands 3 GHz. They are also used as electromagnetic field probes in the microwave bands. Electrically, loops are widely used as a compact transmitting and receiving antennas in the low megahertz range, 3 MHz to 30 MHz. Loop antennas are usually classified as electrically small, C less than lambda over 3, and electrically large, C times lambda. Here, C denotes the loop circumference. The small loops of a single turn have small radiation resistance, less than 1 ohms, usually comparable to their loss resistance. Their radiation resistance, however, can be improved by adding more turns. Also, the small loops are narrow band. Typical band widths are less than 1%. However, clever impedance matching can provide low reflection, transition from coaxial cable to a loop antenna with a tuning frequency range as high as 1:10.1. Moreover, in the HF and VHF bands, where the loop diameters are on the order of a half a meter to several meters, the loop can be made of large diameter tubing or coaxial cable, or wide copper tape, which can drastically reduce the loss. The small loops, regardless of their shape, have a far field pattern very similar to that of a small electric dipole perpendicular to the plane of the loop. This is expected because the small loop are effectively magnetic dipoles. Note, however, that the field polarization is orthogonal to that of the electric dipole. Loop antennas consist of a loop of wire. Loop antennas interact directly with the magnetic field of the radio wave, rather than its electric field, making them relatively insensitive to electric noise within about a quarter wavelength of the antenna. There are essentially two broad categories of loop antennas: large loop or full wave loops, and small loop. Only one design, a halo antenna that is usually called a loop, does not fit into either large or small loop categories. As the circumference of the loop increases beyond lambda over 3, the pattern maximum shifts towards the loop's axis, and when C is almost equal to lambda, the maximum of the pattern is along the loop's axis. Antenna types. Loop antenna. Ferrite loopstick antenna from an AM broadcast radio about 4 inches or 10 cm long. The antenna is inductive in conjunction with a variable capacitor. Forms the tune circuit at the input stage of the receiver. Next is loop antenna for transmitting at high frequencies, about 2 meters diameter. This is a separate loop antenna for AM radio. A 2-element quad antenna used by an amateur radio station. Small loops. The great disadvantage of any small antenna, including small loops, is a very small radiation resistance, typically much smaller than the loss resistance, making small loops very inefficient for transmitting. However, small loops are very effective receiving antennas, especially at low frequencies, where all feasible antennas are small compared to a wavelength. If the loop perimeter is smaller than a half-wave wavelength, the loop must be modified in some way to make it resonant. If resonance is necessary, small loops are called magnetic loops, and if modified for resonance, they are also called tuned loops. Their directionality and radiation efficiency is drastically different from full wave loops. Small loops are widely used as compact direction finding antennas. Ferrite loopstick. Loopstick antennas are omnidirectional around their axis and are primer examples of small loop antennas. They are magnetic analog of the short dipole antenna. They are used as the receiving antenna in most consumers' AM radios operating in the medium wave broadcast band and lower frequencies. Wire is coiled around a ferrite core, which greatly increases the coil's inductance and its effective signal capturing area. The radiation pattern is maximum at the direction perpendicular to the ferrite rod. The null direction of the ferrite core antennas is bidirectional and how much sharper than the maximal directionality. This often makes the direction of the null more useful for locating a signal source than the direction of the strongest signal. The null direction of a small loops can also be exploited to reject unwanted signals from an interfering station or noise source. Examples of small loop antenna. A precision BLF antenna coil operates from 1 kHz to 60 kHz. External capacitors allow tuning. If you add an 0.1 microfarad capacitor, it will tune 13 kHz. If a 0.3 microfarad capacitor is used, then the coil will tune 8 kHz, will work down to 1000 Hz as a general audio pickup coil. Can hear tweaks. If your receiver can null in tweaks loudly with this unit, then you've got a very good receiver. You will go lower if you add more turns. A nice 3.89-inch ferrite rod wound with 139 wire turns and a small capacitor pre-wired to the coil. Upper frequency limit is 60 kHz unless you clip on onboard capacitor. This is an example of BLF antenna coil, and this is the specification of that. Part number BLC 139. The length is 3.89 inches. The thickness is 0.35 inch. The inductance is 1.5 millihenry. The Q is 110. The number of turns is 139. And the price of that is $6.95. Next example is the unit contains two coils. One coil, the green and the red, are the smaller coil. The black and the white are the longer coil. The coils are isolated from each other, but can be connected, make one continuous coil having a top. The above tuning results were tested only with the white and black wires used, the larger coil side. The red and green wires are isolated from larger section and can be used to couple an outdoor long wire antenna. This is AM or LW loopstick antenna is for tuning between 100 kHz up to 1710 kHz. When used with our AM variable capacitor, above this core will the full AM band and down to about 310 kHz. This turning range is the coil centered as in the photo. The specification of that size is 3.5 inches, long by 0.25 inches. The diameter coil the size of that is 3.5 inches long by 0.25 inches diameter. Coil inductance value centered on rod is 788 microhenry. Permeability value EST 125. Ferrite rod antennas. The true loop antenna responds to the magnetic field of the radio wave and not to the electrical field. The voltage delivered by the loop is proportional to the amount of magnetic flux passing through the coil and to the numbers of turns in the coil. If an air core loop is placed in a field, in essence, it cuts the lines of flux without disturbing them in A. On the other hand, when a ferrite magnetic core is placed in a field, the nearby field lines are redirected into the loop B. To get higher loop output is to increase the permeability of the medium by winding a coil wire around the form made of high permeability material such as ferrite rod. Much greater flux is obtained in the coil without increasing the cross-sectional area. AM and FM antennas. The photo is the AM loopstick antenna inside a typical transistor radio. Is very compact and highly directional. The pink-colored wire that makes up antenna is wrapped around a thick ferrite core, the black rod. Usually, as you can see here, there are two separate antennas on the same ferrite rod. One for AM, medium wave, and one for LW, which is long wave. How FM works. If I try to listen a typical radio broadcast on FM frequency of 100 MHz or 100 million Hz, the waves carrying my program are about 3 meters or 10 feet long. So the ideal antenna is about 1.5 meter or 4 feet long or so long, which is roughly the length of the telescopic FM radio antenna. Now, for AM, the wavelengths are about 100 times greater. So, how come we don't need an antenna that's 300 meter or 0.2 miles long to pick up them? Well, we don't need a power antenna. We just don't know it's there. The AM antenna of the inside of the transistor radio works in a very different way to the FM antenna on the outside, where an FM antenna picks up the electric part of the radio while an AM antenna couples with the magnetic part instead. It's a length of very thin wire, loop everything with a few dozen to a few hundred times. Around the ferrite, an iron-based magnetic core, which greatly concentrates the magnetic part of the radio signals and produce a bigger current in the wire wrapped around them. That means an antenna like this can be really tiny and still pack a punch. Without a ferrite rod, a loop antenna either needs many more turns of wire, or the loop of wire need to be a lot bigger. That's why FM antennas for radio sets sometimes take a form of a big loop, maybe 10 to 20 centimeter, about 4 to 8 inch in diameter or so. To summarize, ferrite core antennas known as loopstick are widely used as antennas for radio receivers, particularly for AM broadcast band radios. This is done by winding a coil or loop, generally with tightly spaced turn over one end of a ferrite rod or bar. The ferrite has the effect of concentrating and intensifying the received magnetic field inside the loop. Like other forms of loop antennas, loopstick antennas are relatively free from RF noise, as they react to the magnetic portion of the RF energy received, and they are relatively immune to the electrical components, which is prone to noise caused by electrical sources. In small loop, they are very effective receiving antennas, especially at the low frequency, where all feasible antennas are small compared to a wavelength. Loop antennas consist of loop of wire, interact directly with the magnetic field of the radio wave, rather than its electric field, making them relatively insensitive to electrical noise, with about a quarter wavelength of the antenna. The basic configuration is a powdered iron with a certain permeability. Permeability is symbolized as mu. The permeability of a rod increases the inductance of the coil wound around the rod by a factor equal to itself, the permeability as compared with what the inductance would be if there was no rod inside the coil at all. Loopstick is a shrunk down small multi-turn loop antenna for receiving purposes.